Great. Well, thanks for coming back to the second part of my talk. So I just wanted to remind you of the theorem that we're interested in, which is the following. It says that if surgery on a knot is a null space, then that knot has no essential Conway spheres. So the way that we're going to do this is we need to get a little bit more into the Floer homology. So that's what I want to tell you about next. Now, the key thing here is that we're not actually quite going to study the Heggard-Floer homology of three manifolds. We're going to actually study something called knot-Floer homology, an invariant of knots. So this is due to Schwatt and Szabo, and also due to Jake Rasmussen independently. And the idea here is that it takes a knot in the three sphere and assigns to it the knot-Floer homology of a knot, which is actually just a bigraded vector space. And for us, it's going to be over the field F, which is Z mod 2. And sort of the key principle here is that knowing about knot-Floer homology, this invariant, which is defined, again, in terms of some holomorphic curves or counting solutions to PDEs, this knot-Floer homology tells us something about the Floer homology of the three manifold obtained by surgery. And sort of I'm going to say this in sort of one instance, the instance that we care about, which is as follows. So we'll have the following fact, which is that K is an L space knot. So in other words, it admits a non-trivial surgery to an L space, precisely if a certain condition on the knot-Floer homology is satisfied. Namely, that when we look at the knot-Floer homology of K, it has the following decomposition. So I'm going to write the first grading as the Maslov grading, Mi, and the second as the Alexander grading. The condition here to be an L space knot is that there is at most one element in each Maslov grading and at most one element in each Alexander grading. And the way that our vector space is ordered, the generators are ordered either by Maslov grading or by Alexander grading, are the same strict orders. So that's just a sort of long-winded way of saying that we can index so that the bigradings are both increasing. Now, this is not the usual way that knot-Floer homology of L space knots is written, but this is what we're going to need for our purposes. Let me give a couple examples so that you can have something more concrete in mind. So the first example is that if I take the knot-Floer homology of the unknot, I just get an F in bigrading 0, 0. And so this, by our fact, is an L space knot, and that lines up with the fact that surgery on the unknot gives us a lens space, which is indeed an L space. And I'll say similarly that we can look at the knot-Floer homology of the right-handed trefoil, and it has a more interesting structure. So I'll give you the bigraded structure. It's three-dimensional. And this sort of, again, satisfies the conditions for being an L space knot, and it indeed is an L space knot. We saw earlier that the trefoil has a surgery to L54, which is an L space. So that all checks out. Now, knot-Floer homology is very strong, and in fact, the unknot is the only knot with rank 1 knot-Floer homology, and the trefoil is the only knot with rank 3 knot-Floer homology. So it can detect knots, certain knots, and it is a very powerful invariant for that reason, especially when combined with its ability to tell us something about Dehn surgery. Now, how does this relate to the question about Conway spheres? Well, the key thing about Conway spheres, I'm going to scroll up for a second, is that if we look at our knot that we were looking at before, we look at a Conway sphere, it divides it up into two pieces, an outside and an inside piece. Each is B3 with two arcs embedded in it. So each of these is what we would call a four-ended tangle. And so the idea is that for knot-Floer homology, we can compute the knot-Floer homology of a knot by understanding the two tangles that we might decompose it into. So let me sort of go into more detail about that by following some work of Zebrawia's. So what I mean is that if we have a four-ended tangle, then what we get is a certain invariant, HFT of T, again, a Floer homology invariant. And now the interesting thing is that from our perspective, we're not going to think of it as a chain complex or a homology group. We're going to think of it more geometrically as an immersed multicurve. An immersed multicurve in the four-punctured sphere. And well, we have to be a little bit careful. It comes with some extra data called a local system. But we'll actually just ignore that for this talk. It won't make a difference. And so maybe rather than telling you the method for producing this immersed multicurve, I'll show you some examples so you can see what the structure looks like. So for instance, if I take this trivial tangle here, it's what we would call a rational tangle. The invariant is likewise very similar, very simple. So I'm going to draw the four-punctured sphere without the point at infinity. And so what I'm going to do is the invariant will actually just be this embedded curve like this. Now, I lied to you a little bit in that to specify HFT of T, we need to equip T with a little bit more structure. We need what's called a parametrization of the boundary. Now, it's really not, I'm not going to go into so much detail about what this actually means, but basically it's an identification of the boundary with the four-punctured sphere. So what it means practically is that if we do a diffeomorphism to our sort of three-ball tangle pair, so for instance, we might rotate our tangle by 90 degrees, then we just do exactly the induced diffeomorphism on the bounding four-punctured sphere. So we would just rotate by 90 degrees. And so this is what I mean by parametrized boundary. It sort of depends on how we identify with the four-punctured sphere, but it behaves in a very reasonable way. Okay, great. So this is our invariant for tangles. And now the question is, well, what if we glue two tangles together along a Conway sphere so that we actually get a knot? And the theory is well equipped to handle this as well. So let me talk a little bit about that. And the way that goes is as follows. So let's say we have T and T prime, two tangles, and we glue them together along a sphere so that we have some Conway sphere dividing a knot into two tangles. Well, then actually we can compute the knot Floer homology of this knot, T union S T prime, in terms of the intersections of HFT of T and HFT of T prime. And we can do this in a way that sort of knows about the bigradings. For this talk, I don't want to go into too much detail on that. Maybe we'll just be interested in the dimension of the knot Floer homology. And in that case, what we do is we compute the minimal intersection number of HFT of T. And again, we have to make some minor adjustments to get this exactly right. First of all, we need to have this number. And second of all, we have to do sort of correct for a little bit of an asymmetry, which is that we have to take HFT of T, that immersed multicurve, we have to do a certain reflection in the four-punctured sphere. I'm going to be a little bit hand-wavy and not sort of deal with that issue. But basically, the point is that if we can compute how these two curves intersect, two immersed multicurves intersect, we can compute the knot Floer homology of the union of the two tangles. So maybe what I'll do next, sort of to illustrate this, is I'm going to draw a sort of more interesting tangle, and I'll pair it with one of these simple rational tangles, and we'll compute the knot Floer homology of the result. So I'll try to make a bigger picture here. So let's get this example going. And so I'm going to start with a non-rational tangle. I'm going to start with something called the the 2 minus 3 pretzel tangle. And this sort of has the property that its tangle invariant has 3 closed components. So I'll draw those components. So one of the components is pretty simple. It's kind of just looks like the rational tangle we saw before, but with a little bit of a twist. But then there's some honestly immersed components that we see as well. And these come in a symmetric pair. Great. Now, so that's some more interesting looking HFTFT. And let's say I wanted to pair this with another tangle. So I'm going to pair it with this simple rational tangle to get a knot. And what am I supposed to do according to this theorem is I'm supposed to actually just pair the 2 tangle invariants together and compute the intersection number. Now, conveniently, I've set this up so that the mirroring doesn't really affect this, this blue component. And so the point is that what I see is exactly 2 intersection points. And so therefore, I see that the dimension of HFK hat of this knot is 1. And by what we saw before, the unknot is the sort of only knot with 1-dimensional knot flow homology. And so we see that our knot is unknotted. And you can verify this by just doing a little isotopy of this knot here and seeing that it is indeed unknotted. So we are getting the right result when we're doing this pairing. So this is sort of the basic principle of this tangle theory. But what I want to do now is tell you some more fundamental properties that you can use so that you can actually try to do some computations or study these invariants in a bit more detail. So let me tell you about those. Let's call them fundamental properties. And so there's a few of them that I want to discuss. So the first one is the following. So I'll say it this way: up to reparametrization. So remember, reparametrization just means applying some automorphism to the 4-punctured sphere. So it's basically like doing some Dehn twists along these punctures. So up to reparametrization, every component has a very simple form. Well, in fact, it's basically of the form that we've already seen. So it's either we see a component, one of the components looks like that of one of these rational tangles, so we call these curves rational. Or what we see is one of the green curves that we see above. So I'll just draw that again. Great. And so this is what we'll call an irrational curve. And unfortunately, not every irrational curve is of this form. It comes as this maybe a slight generalization of this. And what I mean by that is it might just sort of wrap around these 2 punctures more times and have some more self-intersections. There's a 1-parameter family of these curves and they can be written down explicitly. But the key thing to keep in mind is that it really wraps around exactly 2 punctures. Just maybe it wraps around lots and lots of times. And so the key takeaway here is that the curves are not too complicated. But I do also want to tell you that this tangle invariant has a lot of good topological information contained inside of it. So let me give an example of this, which is, well, what are the tangle invariants that have exactly just one rational curve and no irrational curves? Well, that's actually easy to characterize. So HFT, let's say, is exactly one rational curve if and only if T is actually itself a rational tangle. So just recall, what is a rational tangle? It's just one of these extremely, extremely simple ones. It's one that's diffeomorphic to B3 with this two trivially embedded arcs. So we're getting some good topological information as well out of this HFT of T. Great. Now, what I also want to tell you about is that we can push this a little bit further to get some more structure to these invariants, both what the curves kind of have to look like, and also sort of what kinds of topology we're detecting. So what I'm going to tell you about next is joint work with Alison Moore and Claudius Zebrawius again. This is sort of the key thing for, or part of the key thing for proving our theorem that L-space knots don't have essential Conway spheres. So I'll tell you sort of two properties. The first is that we can generalize, well, we can sort of generalize what we see above, and that there actually always is at least one rational component. So I'll say HFT of T, in fact, has an odd number of rational components. And that's with this sort of slight technical hypothesis that there don't exist closed components of T, but we don't care about closed components. We assume there aren't any if we're going to glue up two tangles and get a knot. So I'm just going to ignore that. And the other nice detection that we can have here is sort of a generalization of Zebrawius's theorem that the tangle Floer homology detects rational tangles. And sort of the way that that manifests itself is as follows. Let's suppose that HFT of T is only rational curves, all of the same slope. So what I mean by that is that I see a bunch of rational curves in parallel. Now, you might sort of think about this for a second, and if you've thought about the Kuhneth formula in, say, knot Floer homology, you might think this is what you would guess that the tangle invariance of a rational tangle connects sum the trefoil looks like. And in fact, these are the kinds of tangles that, the only kinds of tangles that have this very simple HFT of T. So the theorem is that HFT of T is only rational curves of the same slope if and only if T is what we call a split tangle. So what does split mean? So I'll draw what a split tangle is. Well, it means that it looks like a rational tangle, but we actually tie in some possibly non-trivial knots, or possibly trivial. And the key thing about this tangle is that notice that here's a green curve, which is essential in the four-punctured sphere, but bounds an embedded disk in the tangle exterior. And hence the four-punctured sphere on the boundary is not pi1 injective in the tangle exterior. And so now we're basically able to use this tangle Floer homology to see some of this sort of topological essential surface sort of theory that we started with. And I'll just say something for the experts, which is that the way that one proves this is that you identify tangle Floer homology. Well, you can sort of find a piece of it that is a certain sutured Floer homology of the tangle exterior. And having only rational curves of the same slope actually guarantees that this sutured Floer homology is 0. And so you're working with a sutured manifold which is not taut, and you can use that to find the compressing disk. So that's sort of the key topological input that we need. And now, with that, we're basically ready to prove the theorem. Now, maybe one thing I want to say is I'll leave it as an exercise to try to use these tangle invariants to characterize what are the tangle invariants of a tangle with an unknot closure look like. So I'll just leave that as an exercise because I don't have time to write down that characterization, but it's something you can do, and it sort of gives a very nice structure theorem for tangles with unknot closures. Okay, great. But so with my last few minutes, really what I want to do is I want to just give an idea of the proof of our main theorem. So recall we wanted to prove that if a knot has an L-space surgery, then it does not have an essential Conway sphere. So in other words, we want to prove that if a knot has an essential Conway sphere, then this weird knot Floer homology structure theorem fails that we had earlier. So the point here is that if K, let's say, looks like T1 union T2, so glued along an essential Conway sphere, well, what does that mean? Well, it means that T1 and T2 are not split tangles. Because if they were split, then we could use these green compressing disks to show that the 4 punctured spheres were not pi1 injective into the knot exterior. And so the key thing now is that tells us by our characterization that HFT of T1 and T2 are complicated. So they either have an irrational or some, let's say, non-parallel rational components. But the point now is that tells us actually that these tangle invariants, these immersed multicurves, have to intersect in a lot of places. So I'll just say, therefore, the intersection is just complicated in a way that one can analyze by looking at the bigradings and so on. But that implies that the knot Floer homology of K sort of fails the sort of L-space condition that we wrote down earlier about having this very constrained bigrading structure on the knot Floer homology. And so that's really all there is to the proof. One just has to do a careful analysis of the bigradings and see that it fails this particular structure. So I will sort of end by pointing out to the experts that it seems like we're using something a little bit stronger than the usual notion that the knot Floer homology of an L-space knot has rank at most 1 in each Alexander grading. We're really using something about the Maslov gradings as well, and we actually need to use the fact that there is this total differential on the knot Floer homology, which lowers Maslov grading by 1, for which the total dimension of the homology is 1. And so all of that sort of grading structure appears in this theory, and that's sort of part of the key technical aspects of the proof. But I'm sort of out of time. I don't have the time to go into the details, so I'm going to end